Bismillah ar-Rahman ar-Rahim. We are going to start the second GNG session. I would like to request Mr. Arshad Hussain Palekar to please come on the stage. Mr. Arshad. Can somebody call Mr. Arshad Palekar, please? Thank you, sir. Assalamu alaikum. Please, sir. Assalamu alaikum, sir. So we are going to now start the session. But before we start the session, let me please briefly introduce our esteemed chairpersons. I'll start from Mr. Arshad Hussain Palekar. Mr. Arshad Hussain is a General Manager Exploration and Core Business Development in PPL, a seasoned E&P professional with over 30 years of experience. Mr. Arshad Palekar joined PPL on November 16, 2016 as Senior Manager Exploration SME Specialist Geoservices at Head Office. He was redesignated as SME North in November 2019 to oversee companies operated and partner operated exploration licenses in Punjab and Khyber Pakhtunkhwa. Later, he moved on to the Overseas and Core Business Development Department at Head Office to develop and direct domestic and international exploration strategy and identify business opportunities before his promotion as General Manager, Core and Business Development on March 24, 2023 to oversee Exploration Directorate. Prior to joining PPL, Mr. Arshad remained associated with leading E&P companies as well as service provider for over 20 years to gain a well-rounded experience. He got insight of the complete cycle of Pakistan's upstream exploration, development and production with LASMO, later ENI Pakistan Limited, for 14 years between 1992 and 2007 in various positions. Later, he worked for globally renowned service provider Schlumberger for over 9 years between 2007 and 16 in various management roles, with a focus on providing solutions for client-specific challenges using an integrated approach. It's an honor to have you here, sir. Mr. Irfan Hamid has 24 years global E&P experience in integrated formation evaluation, field development and exploration. He graduated in petroleum geology in 1995 from University of Karachi, currently associated with OGDCL as Manager Reservoir Management. Previously served in Schlumberger, ADNOC, Qatar Petroleum, Dragon Oil Turkmenistan and OMV International. Served in various geographic regions, that is Southeast Asia, Middle East, North Africa, FSU and Eastern and Central Europe in offshore and onshore projects. Mr. Irfan Hamid, it's an honor to have you here as our chair. So, sir, before we proceed on, I would like to request all the participants that you have 20 minutes to present your work. After the 20 minutes, our chairpersons will ring the bell and you will have to cut short your presentation. So try to make it in 20 minutes. So I'll be handing over the participants to the chairperson and they'll be calling them one by one for their presentations. No, sorry. Mr. Waqar Ahmed.
Hello, Assalamu alaikum. The first presenter of this session is going to be Mr. Waqar Ahmed. Waqar Ahmed is currently working in a Pakistan Petroleum Limited as a Deputy Chief Geophysicist in the Exploration Department. He completed his master's degree in geophysics from the Qadim University, Islamabad in 2008 and joined the PPL thereafter. Later, he was awarded the PPL Foreign Scholarship. He completed his master's degree in exploration geophysics with distinction from the University of Leeds in UK. He previously worked on the petroleum prospectivity of the blocks following Lower Indus Basin. He is currently working on the petroleum prospectivity of exploration frontier areas. including Kirthar, Suleiman Fold thrust belts, and Indus offshore. His area of interest are seismic interpretation, mapping, seismic imaging, with a focus on the depth imaging and FWI and seismic reservoir characterization. He is an active member of AAPPG, SEG, EAG, PAPG. So I would like to welcome Mr. Waqar Ahmed for the presentation.
Thank you, sir. Assalamu alaikum. Assalamu alaikum. My presentation is structure, style, and hydrocarbon entrapment mechanism in the Kalat Plateau, Kirthar Fold Belt, and co-authors are Mr. Ghulam Murtaza, Mr. Abud Hussain, Mr. Mudassar Zubair Khan, Mr. Walid Jangiri, and Mr. Umar Farooq. The presentation outline is that I will start with the introduction, then the structural division of the northern Kirthar Fold Belt, then the mechanical stratigraphy of the area, geological map of the Kalat Plateau, structural configuration of the Kalat Plateau on seismic as visible on the seismic, then geological cross-section through the northern Kirthar Fold Belt, field photographs of the Kalat Plateau, regional Eocene depositional isopac map, previous structural models of the Kalat Plateau, and further evidence of Ghazij decalment, petroleum system of the area, and present day stresses and open fractures, and then end the presentation with the conclusions. Kalat Plateau, as highlighted with the blue rectangle on the map on the right, is area of intense deformation, and it falls in the northern part of the Kirthar Fold and Thrust Belt, Pakistan, defining the complexly deformed western margin of the Indo-Pakistan tectonic plate. Most of the work has been published on the frontal part of the Kirthar Fold Belt, and less published work on the Kalat Plateau area, and no prior work which involves the use of seismic data to make the subsurface architecture more clear. So here is a photograph as shown on the map on the right, and from here to the northwest we can see the Kalat Plateau, where mostly Kirthar limestone as highlighted is exposed on the surface. And basically this photograph is from the Kachijal anticline, and here Dunga limestone is exposed, then there is Eocene Ghazij formation, and then plateau area, the uplifted area is there where mostly Eocene Kirthar limestone is present. So this area has surface elevation of more than 2000 meter average mean sea level and has extreme rugged topography. Now we will come to the structural division of the Kirthar Fold Belt, northern part of the Kirthar Fold Belt. So major areas as is can be divided into Sibi Trough, and then as we go in the west, it's the Kirthar deformation front, the frontal thrust part of it, and then towards further west we have interior Kirthar mountain range, and then the eastward buttresses of the Kalat Plateau, which include Parijal anticline, Kachijal anticline, Pataknala uplift, Nugama uplift, and Khuzdarnat, etc. And then our study area, which is Kalat Plateau, it's shown on the map with the blue polygon, and then westward margin of the Kalat Plateau, which is Nali anticline or Gazaband fault, and then further west we have Pashin Basin or Katawaz Basin defines a significant structural depression separating the northern Kirthar Fold Belt from the Chaman Orange Nala Stixley fault system to the west. As any deformation involves that how stresses are in that area and what is the mechanical stratigraphy of the area. So on the right there is our stratigraphy of the area is shown, and we have divided this stratigraphy into three zones. From mechanical stratigraphy point of view, zone 1 is composes of pre-Ghazij rocks, and it includes from Ghazij and rocks up to the Paleozoic rocks. And then zone 2 is composed of Eocene Ghazij shale it is further subdivided into 3 units, which are lower, middle, and upper part. The basal part of Gazij acts as a decalmate zone. Very important aspect of the, when we evaluate the prospectivity at this area and plan exploration well, is the Gazij formation and its thickness, and then the its decalmate, because what happens that this decalmate separate the tectonics which is above and below of it, and the surface, the structure which we find on the surface are not exactly extended to the surface. So we have two different structures which are on the surface, and second one which are on the subsurface. Then the unit 1 of is of lower Gazij, which are marine shales. These are soft and plastic rocks, and because of its lithology, it's act as a decalmate zone. Then the unit 2 is middle Gazij, a deltaic to nearshore claystone dominated lithology with interbedded chalcolithite sand. And then the third part is upper Gazij. So basically clay dominated fluvial lithology, and then its upper more part is marab conglomerates. So here the geological map of the area is shown, and in the yellow color you can see the Eocene Kirthar limestone is exposed in the all the major part of the Kallat Plateau. And from the structures which are mapped on the surface, you can see that these are very short wavelength and narrow structures which are exposed at the surface. And around the plateau, in pink color, you can see the Gazij formation, and then in blue color is the Dungan formation, Paleocene Dungan formation. And Cretaceous rocks are in green color, and Jurassic rocks are in dark pink color. And zone 3, from the surface, one thing you can observe that the Eocene or the structures of zone 3 are shorter in wavelength and very narrow structures. But the structures which are the buttresses of the Kallat Plateau are the deeper level structures like the Parijal, Kachijal anticline. These are large structures. So from the view of the geological map, it's clear that you have two structural regimes from just view of it before going to the seismic of the area. Then we have few field photographs of the area. The first photograph here is chalcolithite sandbeds of the Gazij formation are shown, and these are near vertical beds. And in the second photograph, the small wavelength anticlines within the Kirthar limestones are shown. And in the third photograph, which is below, the box type anticline is shown, which is again in the Kirthar formation. And in the fourth photograph, we have a parasitic anticline within the Kirthar limestone, and then at the bottom, you can see that horizontal beds are present. And in the fifth photograph, there is nearly vertical fault, and then the different layerings again within the Kirthar limestone, it's present. So overall, by viewing these field photographs, you can see that the structural deformation is very intense in the area. As we are close to the hinterland, and the stresses are acting hugely in the area, and they have deformed the Kirthar limestone and the Gazij limestone present in the this Kallat Plateau. Then as we are more concerned about the Gazij formation at its thickness, because all our targets underlie it. When we viewed the isopac of the vintage isopac map of the area of Eocene rocks, it shows that when we go to the western area, anomalous thickness of Eocene rocks is reported. So as shown in the study area, 1 to 3 kilometer thickness of these Eocene rocks is reported in this area. But as we go to the cross sections in the next slides, we can see that the researchers which have worked in the area, they have not taken into account the variation of Eocene rocks, especially the Gazich formation, while making the cross sections. So this is the Colombo Plan geological map and cross section of 1961, and the location of Kalat Plateau is shown here. And here the Kirthar formation is shown in the blue color. And you can see that they had not extrapolated below Kirthar that how thickness of various formation is changing, or what are the structures extending below it. But overall, other than the plateau, they have shown like this. Here is the Chiltern limestone, but they have not modeled in this area. And this is the structural cross-section prepared by Mr. Daniel Schelling in 1999. And here, again in the yellow, Kirthar limestone is shown, and in orange color is the Gazich formation. And you can pretty much constant thickness of Gazich is taken, and the structures which are below, they are exactly at the surface anticline location. So what they are doing, they are projecting the surface structures to the subsurface. So what they have done, they have taken the constant thickness of Eocene Gazich formation and added their sedimentary units below the Kalat Plateau. So this is very important that whether your surface anticlines are extended to the subsurface or you have different structures in the subsurface. So previous work as shown here is extrapolating or extending the surface structures to the subsurface. And this is another cross section. This is basically third party PPL unpublished internal report of 2015. So they have not taken into account the decalment within the Gazich formation. So they are also extending the surface structures to the subsurface. So basically all these studies they are not taken into account the seismic data which was not available at that time, and what seismic has shown us we will discuss in the next slides. And here is the seismic line, which is regional seismic line, which is shown in the red color here. And you can, this is the position of point here, A dash, and this is A. And you can see that this is the Kirthar formation, which is exposed at the surface at the Kalat Plateau location. And then the thickness of this is Gazich formation. And below Gazich formation, in orange, you have Dungan formation, and blue in the top of Chiltern limestone. Okay. So you can see that there is abrupt variation within the Gazich formation, and the surface and subsurface structures are totally disconnected, and this is the interpreted decalment at the unit bottom mass unit of Gazich formation. And here is the extended geological cross section to the Kalat Plateau. And you can see that same thing is shown as this is Gazich formation, and zone 1 structure are deformed uniformly where we have steeper faults. But when you go to upward the decalment, what is happening that we have imbricate thrust system, and they are a relatively gentle fault which terminate in the bottom part in the decalment, basal decalment. And then one further evidence of the decalment is the FMI data of Valley. Valley is the basically first discovery through this plateau. And you can see in Gazich, you have abrupt variation in dips because of the flow nature of this Gazich formation. But when you go in the pre-Gazich rocks, zone 1 rocks, we have very gentle dips. But we are observing on the surface, you can see same in the FMI data that these are gentle dips at this level. And then we come towards the petroleum system of the area, and from the basin modeling, we can see that Gazij formation, which is also a top seal, is also source rock, acts as source rock in the area, and it's in the oil to wet gas generation window. And from this grabens, it charged the structures in the upthrown structures. And then other source rocks are also there, which is Mughal Code Moro, and then the Triassic rocks. And then present day stress regime, the area is in present day in the strike slip regime. And what happened that you have the SV is the sigma 2, it's the vertical. And then the stress is maximum horizontal stress orientation is the northwest to southeast direction. And these are low matrix porosity reservoirs to mainly flow to the fractures. And fracture orientation is also same as the maximum horizontal stress orientation. And these are the critically stressed fractures. These are open and flow. And these are the strike slip faults interpreted on the surface. So now we come toward the conclusion slide. The Gazij decalment is very important, and it separates the structuration above it and below it. And the structuration of the Kalat Plateau is majorly influenced by the mechanical stratigraphy in the area, in which the Gazij formation plays a key role through its lithology and depositional thickness variation. Major structural deformation in Kalat Plateau occurred after the deposition of Kirthar limestone and simultaneously deformed strata above and below the decalment. The structural framework of Kalat Plateau presents great potential for hydrocarbon entrapment. The Gazij shale is responsible for the development of decalment and also act as regional topsoil in the area. In other parts of the Kirthar fold belt, especially in the frontal area where we have several other blocks, the main thing to look after is the thickness variation of the Gazij, because where we have significant thickness of Gazij present, and especially it's the bottommost lower Gazij unit, the presence of decalment needs to be confirmed prior to the drilling of exploration wells. The apparent thickness of Gazij can increase manifold due to tectonic thickening. And we acknowledge the PPL management for their permission to allow to show our work and data. So any question, please?
Thank you very much, Waqar, for your presentation. Just to keep the schedule on time, I would request audience to have 3 questions. Yeah. Thank you.
Ji, Dr. Sahab.
My name is Dr. Sajjad. You have assumed a basal decalment within the Gazij. But I was looking at the cross section that towards the hinterland, and this decalment is doing nothing. No structuration and no involvement of these older rocks, Dungan and older. So how come this can happen? I mean, what are the geological evidences of this decalment, and why this decalment is doing nothing with the lower horizon, at least in the hinterland side?
Thank you, sir, for your question. Actually, this the hinterland of this particular basin, the Kalat, where Kalat Plateau is present, was the depot center of the Gazij formation, and all the Gazij is deposited in this part. As we move toward the west, there is a hinterland, just a boundary fault we have seen over there, like the Kalat fault. So toward the east of that, the main Gazij depositional system was there. So the decalment is within that particular part, only exists in nearby the Kalat. Even if we move toward the eastern side of Kalat Plateau, where the thickness of the formation is about 1,000 or 1,200 meter, there is a very good symmetry, and based on that, the previous work, the people have seen that the Dungan and the Kirthar formation have the same dipping slope over there. So, but when we drill the well and see the FMI data and drilled our structure beneath that particular Gazij formation, there we see the difference in structuration. And based on the seismic data, those are separated from the structuration which we have seen in particularly in the Kirthar and Gazij part, particularly in the central part of Kalat Plateau. So that is why you are absolutely right. It's not doing something which it should do toward the west, because the Gazij thickness is also decreasing as we move toward the west, because that is its providence area.
ये
Thank
स्लाइड के ऊपर ये आप बता सकते हैं स्लाइड के ऊपर जो है
So on this particular slide, if you see, so almost parallel like that. So in the hinterland side, toward this side, Gazij was not deposited. Some kind of over-interpretation we have done, particularly in this area, but the seismic data in this particular place was not good enough to give us some more confidence how this margin is actually developed. So in future, we will see that how that particular part is would be developed. So
I would like to say something, that this decollement is for sure coming from west, from the B side. You can see, look at the section, and it is strangely coming from side B, from west.
Yeah.
But in the west, it is doing nothing totally. So
particularly this part.
Yeah,
this,
west of your hand, where you
toward this
yeah.
side, because there is no Gazij.
Okay,
There is no Gazij.
So how come this decollement, where it originated actually? I don't see the origin of this decollement. It is just a decollement, a line tipping along a fault in the west, and then nothing. It should be logically interlinked with the older strata below Gazij, if you look at that. Plus there is a lot of displacement is supposed to happen along this decollement, and I don't see any match. There is a total mismatch between the upper structuration and the lower structuration. Thank you.
So in this particular sense, when we have seen we have used break thrust and folding in the structures below this decollement, and those are might be in the earlier stages. There could be a normal faulting over there. Those have been overcome by the folding and then break thrust. So if we have when we have restored that particular part, the upper and the lower, the earlier sections we have seen, in those one the people do the same thing, like the similar kind of restoration in the below decollement and above decollement. They just restore and try to match those things. But what is our point over here? This fault is the boundary thrust, and beyond toward the west of this one, how much how much movement has occurred along this fault, that is not sure. That is why I said there is some over-interpretation from our side, particularly in this area. The rest of is the fold we have constructed based on the surface, and the fold, the break thrust, Hamming fold, larger fold beneath this decollement we have proposed. So those are based on the seismic data. So we have observed the highs and lows on over there, and then we have mapped those one or construct over there. So if we see any kind of mismatch above and below the decollement, that could be due to this fault. This fault is not like it is now over here. It should have been more complex, because there was an issue when we were constructing this section. That's how this Gazij is, we have to limit here. So there is a exposure over there older than the Gazij. So we don't know exactly the above this particular structure how much thick Gazij previously was there. So all the strata is eroded.
So it's a
to actually define this decollement within the Ghazij. And as far as this interpretation is concerned, I agree with this interpretation. But as the Dr. Saab is saying that as we are moving further west, there is something different. So the additional data, additional cross-sections in this area, maybe next year
So
will further add value to this.
For
phenomena.
that, you can see some few lines we have given below. So that particular seismic line shows some sequence of deformation. So you can see some pinching out strata over there. So those are the evidence.
Thank you. A very good explanation.
And also, what is happening that towards the west, we are towards the end of the Ghazij basin, where deposition actually started to happen. And what the point we showed the previous cross section, that this is the seismic line. And beyond this, like when you are looking at the where Ghazij is terminating, it's basically extrapolated from the surface geology. It's not based on the seismic data. This is the seismic, and this is the seismic. You can see that the Ghazij thickness is decreasing, that we are towards the margin of Ghazij basin, but where it's the older rocks are exposed at this area, it's not based on seismic, it's based on the surface geology. So it may not be perfect as per the previous cross section, which are solely made from the surface geology.
I think structural geology, as complex as we have in Pakistan, will take the whole day. So, but I think it's a very good attempt, and there is always room for improvement as well. So, thank you very much. Thank you.
Thank you, sir.
Second paper is from Mr. Shadab Ali Quraishi, titled Enhance Imaging of Complex Fault Structure to Reduce the Uncertainty in Fault Interpretation. So a brief about Shadab is received his BS in Geophysics in 2012 from Bahrain University, Islamabad, MS in Geophysics from the Bahrain University, Karachi. He has 10 years of professional experience in the E&P sector, joined United Energy Pakistan as a graduate trainee geophysicist in 2013, and currently working as a reservoir geophysicist in subsurface team. His key areas of interest are seismic interpretation, velocity modeling, prospect generation, and validation through seismic attributes analysis and integrated reservoir characterization. Over to you, please.
Thank you, sir. Assalamu alaikum, everyone. I am Shadab Ali, and the topic of my presentation is enhanced imaging of complex fault structures to reduce the uncertainty of fault interpretation. In this, we will discuss the examples from lower Indus Basin of two fields where we have used a relatively new technology of fault likelihood to interpret subtle faults which were forming compartmentalization within the field. So in order to drain the separate compartments, these small faults are very crucial. The co-authors for this paper are Numan Ali and Tajammul Khan and Kashif Khan. Kashif Khan is associated with Halliburton, whereas Numan and Tajammul is associated with UEP. Okay, so the table of content of my presentation is, first of all, we will talk about the study area, the tectonics of the study area and the stratigraphy of the lower Indus Basin. And then we will move towards the fault likelihood attribute. We will probably discuss small theory and algorithm of the fault likelihood. And then we will move towards the examples of lower Indus Basin, of two fields from lower Indus Basin, where we will discuss the structural configuration, and we will compare the fault likelihood attribute with other structural attributes, and in the end we will discuss the conclusion of this presentation. So the study area is located in the northeast part of the Pakistan, in the lower Indus Basin. The structural style and the the tectonics events that are governing the structural style and the sedimentology of the lower Indus Basin are basically the rifting of Madagascar and Indian plate, which started in from Jurassic to Cretaceous. This caused a rift system in this area where the general common structural style is Horst and Graben, and there are some sinistral strike slip faults present in this area as well. So this is a simplified cross section of lower Indus Basin where it is showing the tilting and the rising of basement towards the east, and the thinning of the sedimentary structures, and the frequency of the fault in the east is very low, whereas in the steady area, which is located in the west of this, is where the sedimentary package is also thick, and also the frequency of the fault is relatively higher. So this is another example of the lower Indus Basin cross section, which is showing the similar thing with source, reservoir, and seal mentioned. So the overall stratigraphy of lower Indus Basin is fairly understood, that mainly the source rock of this area is Sambar formation, whereas the reservoir in this region are lower Guru formation, and mainly the seal or the cap rock is the upper Guru formation. So moving towards the fault likelihood, we all know that delineation of complex faults to identify undrained compartment in an area which is covered with 3D seismic but having low signal to noise ratio is a challenging task, especially when we are working on traditional methods of picking faults. Even the traditional attributes like curvature, coherency, and discontinuity, these all are two-dimensional attributes, but they do not provide much help in an area where the seismic signal to noise ratio of the seismic is low, and in an area where there are steep dips present. So the main objective of this study was to identify small-scale faults or splay faults which have critical role to generate undrained compartment, so that we can better exploit the reservoir potential of the field. So moving towards the theory of the fault likelihood, actually the fault likelihood attribute is based on structural oriented semblance and is capable of detecting faults with throws that are less than seismic tuning thickness. Because it detects faults as a change of reflector coherence as rather than a typical identification of discontinuity or offset of set of reflectors. So this is an example of how fault likelihood actually detect a fault. So for example, this is a blue line is a fault present in the subsurface where we want to calculate the fault likelihood at this black dot. So the semblance will be calculated at elongated discrete set of dips, and where the semblance is minimum and the fault likelihood is maximum, this location is saved. So we can also define fault likelihood as an inverse of semblance, where the semblance is minimum, fault likelihood is maximum. So fault likelihood is actually the likelihood of presence of any fault in an area. So this is the these are the steps which are involved in fault likelihood algorithm. Whenever we generate a fault likelihood attribute, in the back end it generates all these 7 volumes, so that and give us the final thinning volume and the tracking volume. So I'll go briefly through all of these algorithm working. So first of all, whenever we generate fault likelihood, it generates live volume. So in live volume, it remove all the blank or null spaces from the input seismic data, and so like it generate a volume that is like fault free. Then smoothing filter volume is generated. It helps the computation of semblance to keep stable, and we generally use longer smoothing lengths for structural features like the faults, and use shorter smoothing lengths for stratigraphic features like channels. Secondly is the slope volume. This volume is basically generated so that we can remove the effect of the dip from the data. So it aligns the traces so that any coherent events are horizontal, and it generates two volumes, both for inline and cross lines. After these steps, semblance is then computed at very small number of adjacent seismic volumes, seismic traces, and lastly, the fifth, this is the main step of the fault likelihood, which we have also discussed in the previous slide, that it determines the location as well as the orientation of the fault, and it is the most computation. It takes most of the computation time, and output volume from these scanning volumes are fault dip, fault strike, as well as the likelihood volume. So likelihood volume is actually what we are actually looking for, but there are two additional volumes in this algorithm, which are thinning volumes and the tracking volumes. Thinning volume is just the scanning volume, but these are the ridges and the clean version of the scanning volume, so that we can see a more sharper fault in the seismic data, in the fault likelihood attribute, as compared to other structural attributes we have. Tracking volume is the final volume, which is the scaled volume at certain combination of dips and strikes. One additional application of fault likelihood is and of tracking volume is that it can be used for automated fault interpretation, but this was not the scope of the study, so that I will move towards the main objective of this study. So this is an example from lower Indus Basin, field A, which was discovered by the drilling of Alpha 1 well. This well has encountered around 163 feet of net pay, and the initial production was around 1400 barrel of oil with 0.8 mmcf of gas. This field is located at the downthrown side of the main fault, where the throw of the main fault is around 200 feet, and the dips and the dip of the strata is very high, and in some of the wells the FMI data also indicated around 15 degree of dips. And because this field is present at the downthrown side of the main fault, the intensity of the splay faults near to the main fault are very high, and these are also very crucial, as these are creating separate compartments which are isolated from each other. So identification of these splay faults were very crucial. So in order to drain the full potential of the hydrocarbon from the field, but this was masked by the presence of steep dips in the area. So fault likelihood was generated on this area, and which helped us in highlighting the splay faults that were sharp, and the effect of the dips were eliminated. I will show, so this is the depth structure map of the field A. So we can see there are several splay faults which are both antithetic and synthetic in nature, present with the main fault. And now I will show you the, sorry, I will present, this is the cross section of area where field A is present. So the overall structural style, we can see that the overall structural style is horst and graben structure, and our field A is present at the graben side of this main fault. So this image is again a zoom version of this area. We can see approximately 3 splay faults associated with this main fault, and the dip of, and there is a very steep dip present at the reservoir level. So next is the comparison of fault likelihood with other structural attribute. This image is the time slice at the reservoir level, and likelihood is shown on this image, whereas on the next image discontinuity attribute is shown on the time slice. Now here we can see the on the discontinuity attribute, because of the higher dips in the area, the splay fault identification is masked by the very in the form of a zone, and we cannot see any sharp boundary of any splay faults. But on the fault likelihood attribute, we can see very sharp boundaries of splay faults, which helps us to easily pick the faults and also highlight the undrained compartment in the field. On the right, the similar example is shown with seismic section overlain by fault likelihood and seismic section overlain by discontinuity attribute. Here we can also see the darker region, which is showing in the form of a zone where the splay fault is present, and this darker region is basically because of the steep dips present in this data. However, on the fault likelihood attribute, we can see a sharp boundary of splay fault, and we can easily mark the splay fault based on the fault likelihood. So the results and outcome from field A is that fault likelihood helps in identification of faults which are present in the downstream part of the main fault, and these were actually masked by the strong dips in other attributes, other normal structural attributes, which are discontinuity or semblance. And because it measure in the in structure oriented semblance, so the effect of the dip was removed, and it helped us to identify compartments which are separated from each another. So the mapping and the extension of these splay faults help to identify undrained compartment, so to improve the recoveries of field A, and this will also help to avoid drilling surprises in the future development wells of field A. Next is the, so this is the likelihood attribute at the time slice overlain with the fault polygon of the field, reservoir field. Okay, here we can see that the fault interpreted fault polygons are tying with the discontinuity shown on the fault likelihood attribute, which are very sharp as compared to other attributes. Next is another example from field B. Field B was discovered by drilling of B1 well in lower groove formation. The well produced at an initial rate of around 9.5 mmCF with 928 barrel of condensate. This is also a downthrown field where multiple splay faults were encountered in the well, but these were not visible on the seismic section because the seismic was fairly continuous in this area. So in order to exploit the potential of in this field, a B2 well was planned, which was planned to be drilled an updip location from B1 well. B1 well was actually producing water, but the B2 well came deeper than the prognosis. But however, open hole logs suggested 90 feet of pay in B2 well, and dynamic data also suggested that B2 well is situated in a separate compartment. But this line is showing a seismic line, a cross line passing from B1 to B2, and here we can see that there is no indication of fault rather than a sharp change in the dip. This is the fault likelihood attribute which was extracted in the field B, and here we can see northeast southwest oriented splay fault which was not visible on the discontinuity attribute. So these subtle fault with having throw of around 20 feet was picked on the base on fault likelihood attribute, and there was no indication of this splay fault on the discontinuity. Coming towards the result and outcome, so the drilling results of B2 suggested that there are splay faults present in the area which are creating compartment even when the throw of the fault is very less and they are juxtaposing sand against sand. So actually these splay faults are sealing in nature and they are below seismic resolution, or so, but we were able to pick them based on the likelihood attribute. Likelihood attribute also helped in identification of these splay faults even when the seismic reflectors were fairly consistent and continuous. Uh, these faults were not visible on other attributes like discontinuity, curvature, or semblance. And mapping and extension of these splay faults would help in future to drain from compartments which are isolated from the existing ones. So here we will also, there is another comparison of discontinuity attribute with the fault likelihood attribute. The fault polygon is overlain with the on this image on this time slice. Here we can see there is no indication of splay fault on the discontinuity volume, and we can also see the fault likelihood shows a very sharp boundary of the fault cut as compared to the discontinuity, which is showing a broad band of the fault zone. So this is the depth structure map of the field. On the right, this is the pre-structure model, and whereas on the left, this is the post-structure, post B2 well model. Here we, based on the well data information and integrating with the dynamic data, we have picked this splay fault, which is separating B1 from B2. So in the end, the application of fault likelihood technology in the lower Indus Basin has produced results that change the perspective of fault resolution in 3D. Fault likelihood allowed us to map splay faults in an area where the steep dips is the problem, and these and normal structural attributes were not helping in that area. Also, fault likelihood also helped to pick small faults which were not visible on other structural attributes. The main drawback of other approaches is that they measure semblance or disorder over a region that is unrelated to the orientation of the fault, whereas fault likelihood measured not only the location but also the dip and the azimuth of the fault. The only drawback of the fault likelihood is that because it operates on structural oriented semblance, so it is very computationally time taking, and so it takes a lot of time to generate fault likelihood over a region in 3D seismic. Lastly, these mapping of the location and the geometry of these splay faults not only help us to improve the recovery of the field, but also safe and safe drilling for future wells in any field. Thank you. In the last, I would like to thank management of UEP for giving the permission to use the data and present this paper. And I will also like to thank my colleagues. So, thank you.
Thank you, Shadab, for your paper. Now the floor is open for the question and answer. We'll take only 3 questions maximum.
जी अस्सलाम वालेकुम. This is Etisham Faisal from United Energy. First of all, this was a commendable presentation. My appreciation to Shadab. I just want to understand one thing. Basically, you have mentioned that these are the high angle faults, and probability of the upthrown side where we have signal to noise ratio have more impact over there rather to the downthrown side. And because of number of faults which you have highlighted, it somehow deformed the strata. So based on the this fault likelihood attribute, it helps you to identify actually the compartmentalized zones. So what is your understanding on the upthrown side? I mean, this data is more useful on the upthrown side, or relatively downthrown has a more better results?
So actually, as we have discussed that both of the fields were downthrown fields, and on the upthrown side, the intensity of faulting is not as great as we have seen in the downthrown part. But obviously, the signal to noise ratio in the upthrown part is much better than in the downthrown part, and these will fault likelihood attribute produce more better results in the upthrown as compared to where signal to noise ratio is less.
Okay, there's no question, then
It's Parvez Bhatt with Virtual Petrophysics. Before drilling B2 well, have you considered doing a VSP survey to be sure about these salt faults below the seismic resolution?
No, actually, based on the seismic data, B2 was planned to be drilled up dip to B1 well. But because of error in depth prognosis or velocity anomaly, B2 well came down dip to B1, and at that point B1 was producing water. So like we actually thought we are going for the attic, but we came actually down dip. But the open hole results shows that B2 well encountered 90 feet of pay, and the dynamic data also suggested a separate fault block as compared to B1.
I understood that you drilled the B2 well based on your likelihood of faults.
No. So actually, after the drilling results of B2, because it was the down dip well to B1 and it encountered 90 feet of pay. So in order to resolve this issue, we actually generated fault likelihood attribute so that we can have a look for any barrier or any fault between B1 and B2.
Okay, understood.
Yes. In the B2 well, yes.
okay, thank you very much, Shadab. Now the third paper is going to be by Mr. Javed Iqbal. The paper title is Impact of the Low Frequency in Imaging Deeper Targets in Haran Basin. Brief about Mr. Javed. Javed is currently working with the PPL as a senior geophysicist. He completed his master's degree in geophysics from the Qasim University, Islamabad, joined PPL in 2011. Later on, he was awarded a foreign scholarship, completed his master's degree in geoscience from the University of Stavanger, Norway. He previously worked on the petroleum prospectivity of the basin, Badin area of the lower Indus Basin. He is currently working on the petroleum prospectivity of exploration frontier areas, including Haran, Four Arc Basin, Makran Basin, Suleiman Fold, and Thrust Belt. His area of expertise: seismic interpretation, mapping, seismic imaging, seismic facies analysis, and seismic reservoir characterization. Over to you, Javed.
Thank you, sir. So, respected chairman, dear colleagues, Assalamu alaikum and good afternoon. Impact of low frequency in imaging the deeper targets in the Haran Basin. So, this is not a new technique, and it has 2 decades with different names like broadband seismic, high resolution seismic surveys, and the latest one is the low frequency seismic survey, which we have done in Haran Basin. So the co-authors for this presentation, for this paper or presentation are Mr. Atif Mir, Mr. Waqar Ahmed, and Umar Farooq. So coming to the agenda of this presentation, we will start with the introduction of this presentation, and then we will go to the objective. What are the objectives of this presentation? Then we will talk about the low frequency surveying, some basic things about this low frequency surveying. And then we will discuss the role of low frequency in imaging the deeper targets, which will be followed by the improvements we get from the low frequency surveys. And then we will present some one analog from South Oman. And then we will discuss some offset, seismic offset considerations in addition to the low frequency use of low frequency. Then we will move to the precautions of using low frequency surveys, and then we will conclude the meeting with the conclusions. So the study area is located over here, which is marked with the blue rectangle. So it is bounded by Rasco Range to the north and Sihan Range to the south over here. And it is bounded by Chaman Fault to the east, and it extends into Iran in the west. So more than 400 line kilometers of 2D seismic data has been acquired in this basin, including this campaign. And finally, we have got something at the target level. We have got some resolution of seismic reflections at this level, which we will be discussing in the coming slides. So on the right side, we have this stratigraphic chart for the Kharan Forak Basin. And for the Paleogene section, which is the prospective stratigraphic section in the Kharan Forak Basin, it is composed of at least 4 unconformities in this area, which the U1 is the oldest one, and the U4, unconformity 4 is the youngest one. So the problematic area in this basin is between this U1 and U2. I don't know why this pointer is not working over here. So package 5 and package 6, which is falling between unconformity 1 and unconformity 2. So on the seismic section, you can see that the blue one is the top package 6 and the green one is the top package 5. And in between, you cannot see anything on the seismic section. So this is a line from a previous seismic campaign. So this was the main problem that we went for the low frequency seismic survey, and we got some encouraging results, which we will present in the coming slides. So before embarking on the results and analysis of the data, so this is something about the low frequency surveying, and we can see that on the top we have a cartoon over there for the frequency spectrum. So this frequency ranges from 10 Hertz to 80 Hertz, and it basically shows that what is the octave. So octave is simply the doubling of the frequency. So if we have from 10 to 80 Hertz, it will composed of 3 octaves of seismic data. So on the low frequency end of the seismic frequency spectrum, we have some issues of recording too much noise, which we have to manage when we are planning for the low frequency seismic surveys. But on the other hand, on the high end of the frequency spectrum, we have a lot of attenuation of seismic frequencies, and we cannot go to the deeper part for imaging. So that is why we have to extend over low frequency spectrum to the lower side of the bandwidth. So in the bottom we have modeled some wavelets using different octaves of seismic data. So if we see this cyan color, which is 1 octave data from 8 to 16 Hertz, green color wavelet is for 8 to 32. This is 2 octave wavelet, and this red color is for the 3 octaves, and the blue is for the 4 to 80 Hertz seismic data, which is more than 4 octaves. So by adding the low frequencies, we have got results, and we have improved the resolution, which is coming in the upcoming slides. So this is the comparison of frequency spectrum of 2 vintages 2012, which we acquired in 2012, and the red curve is for the 2022 vintage. So we can see that we have pushed the frequency spectrum to the lower end of the frequency. In this survey, in the recent survey, we used low frequency equipment like low frequency vibrators, which were able to generate a frequency spectrum of 1 to 250 Hertz, and geophones, which can record down to 22.5 Hertz of low frequency. And then by recording this 4 Hertz of frequency, we have added 1 full octave of the frequency in the frequency spectrum. And by that, we have got some deeper penetration in the seismic data, and we have resolved the reflections over there. So coming to the more comparison for the seismic wavelets, so we have the green. This green wavelet is for the 2022 vintage, and red wavelet is for red wavelet is for the 2012 vintage. And in these wavelets, we can see that because we are using 4 to 80 hertz of frequencies for the recent survey, we have got the wavelet a little bit sharper than the previous one, and plus we have reduced the side lobes for this recent data. So these two effects are very important for the resolution of the seismic data, and for the better coherency and better reflector continuity in the seismic sections. So in the bottom we have examples from the recent 2D seismic data. On the right side we have a seismic section for the 2022 vintage, and on the left side we have a section from the 2012. So there is an overall improvement. The section is more crispier for the recent seismic survey. And for the comparison, I have highlighted the area which is the most relevant with the red rectangle, and you can see that the reflections are more continuous, more coherent in the recent seismic data. So coming to some more analysis of seismic data. So we have these unflattened CMP gathers from comparison of the unflattened CMP gathers from 2012 and 2022 vintages. So on the right side, on the top upper side, right side, we have CMP gather unflattened from 2022 vintage. And on the left side, we have the same gather from the 2012 vintage. And you can see that around 4 seconds, we have bright amplitudes of the reflections at that location, so which is not visible in the previous vintage. Similarly, for the semblance plots, we can see the same situation on the semblance plots. On the right side, on the lower right side, we have semblance plots for the 2022 vintage, and on the left we have 2012 vintage, and we can see that the semblance is very bright for the around 4 seconds, which is the target area in this basin, and the same is not that in comparison is not that bright as is the lower frequency in the semblance plot. So moving next. So this is some more analysis of the seismic data for the low frequency and vintage seismic data. On the right side, this is a composite line for the two seismic lines, one from the 2022 vintage and the other from the previous vintages. So you can see that around the target area we have better reflection at the target levels, like for the package 6, which if I can point out with this pointer over here. So that is more coherent, and reflector continuity is better on that side. But on the other hand, when we come to the left side, which is a vintage seismic, the continuity and coherency of the reflector is not that good, and we cannot. There will be difficulty in interpretation for sure if we interpret the left side seismic section. So in addition, we have also resolved some additional packages inside package 5, which I have highlighted with this pink arrows over here. So these are the additional packages which were not resolved in the previous seismic campaigns. So all of this shows how important is the low frequency content of the seismic data. So that can give us that can help us in interpreting the key horizons and mapping all those things. So now coming to the examples from the Haran Basin where we applied this technique. So on the right side, this is the recent seismic section from the recent seismic campaign, and on the left side we have from the previous seismic campaign, and we can see that we can trace this package, top package 6, with confidence. However, on the other side, when we come to the previous vintages, this top of the package 6 is not that easy to interpret, and we have to go for the if and buts. And Similarly, you can see that on the previous vintages we have very little reflections over here, and there is no pattern in these reflections over here, and they don't make any geological sense actually. But on the other hand, when we come to the recent seismic data, which is the low frequency seismic data, we get some reflections, and we get some patterns, and we can follow them, and they make much more geological sense. So that is one of the advantages we got from low frequency surveying. So this is one example from South Oman. So this data was recorded using frequency bandwidth of 1.5 to 86 hertz. And you can see that I have marked some significant improvements on the left side. This is the low frequency stack, and this is the legacy stack from the conventional seismic. So I have marked this prominent reflection over here. But overall, you can see that there is an improvement in the seismic data from top to bottom for the low frequency seismic. So because in this campaign we had a far offset of 8 kilometers, so that to eliminate that impact, we have processed this recent seismic data with the offset of 6 kilometers and compared it with the 8 kilometer offset original data, and we can see that there are in the 6 kilometer offset section we still see the pattern in the seismic reflections, and continuity and coherency is better. It means that the far offset has an impact, because we have introduced some random noise in this section with 6 kilometer offset, but still we are getting some improvements with the using of low frequency in this survey. So we have to be vigilant about using the low frequency surveying. We should do rigorous testing before embarking on the how far you should go to the lower end of the frequency, because the low frequency noise can be very so the low frequency can harm your shallower section of the seismic data. So on the top you have this legacy stack, and we can see that in the shallower sections we have the coherency and the reflector continuity is better. But in the shallower section, in the low frequency data, we can see that these patchy random noises, and at this location and these locations, so which are the drawbacks of the low frequency at the shallower sections. So if your target is very shallow, so then you should do the testing that if it is not harming your shallower targets. But in the Kharan Basin, we had deeper targets below 3 seconds, 3.5 seconds. So we did not have that problem. So we went for 4 to 80 hertz of frequency spectrum. Moving next, conclusions. The resolution of seismic data is very important for better continuity and coherency of seismic events. So we all know that it is helpful in interpretation of key horizons, generating maps, and ultimately maturing the drillable prospects. So by adding the low frequency to the spectrum, we get better, deeper penetration of better energy, and we get improved seismic resolution. So we have applied this technique in Kharan 4-arc basin to image package 5 and 6, and we have got some successes in that. So this technique is recommended to be utilized in the similar basins and settings, but after a proper testing. So for the future work, we are planning to use this low frequency seismic data for depth imaging using full waveform inversion. So we would like to acknowledge the support of PPL management and for allowing to present this work at this forum. If you have any questions, the forum is available.
Thank you, Javed.
Javed, 1 minute, please. It was a very good presentation. I was, a little confused, Javed. I just want to understand, this topic of discussion, do we address at the time of acquiring new seismic data? We need to place low frequency geophones over there with the control low frequency vibrator we can use to acquire the data?
Yes. Actually, first you have to mark that what is your target. That in the Karan Basin, in this case, we had a package that we were not able to resolve. So we marked that, and then we planned for the low frequency that maybe this technique can help us. So we went for the low frequency vibrators and geophones and recorded that data with low frequency. So that, yes, you have to deploy geophones and.
So actually, I was, just curious to understand. The way you have explained, yes, it is making a sense. Now the point of concern is, the geometrical spreading in absorption coefficient effect. What we understood once we blast the source, the frequency which is moving away from the source, going deeper section for the deeper dive in the strata, it is decaying.
Yep.
From away from the source. So do we think once on a particular reservoir target of interest which we are going to map it, for some reason over there you could have a low frequency relatively with a shallow section, you could have a higher frequency. So if let's say like you show us your amplitude spectra, that's very clear that there is a ringy phenomena which is indicating a very high frequency noise is there on the amplitude spectra. Yes, this one, there is a very high frequency, ringy noise is there, and this even makes sense to us, especially in an area of fold and thrust belt regime. You have a very high frequency noise contamination in the data because of the complex geology over there. Now, this can be figured out, like you have mentioned, maybe with this technology, or we can figure out this thing. Kind of a post-processing, effect. If you can just take amplitude spectra, you can identify from where this ringy phenomena is coming out. If you can clip that, you could have a low frequency within the existing seismic data. Yeah. So again, it has a similar, kind of a statistics. I was a bit confused. If let's say that's fine with the new technology of implementing with a control source. With the low frequency, we can inject inside the subsurface along with the low frequency geophone technology. But with the existing available seismic data, we could have again, a lot of problems over there. Mm-hmm. So do you think that maybe by applying certain cutoffs, preserving relatively low frequency in the amplitude spectra will also help you at the time of interpreting the data?
Yeah, thank you for the question. So the first thing is, if you are deploying, let's say 10 Hertz geophone, you are not recording low frequency data over there. So first you need to record that, then you can process that. So otherwise, there are some processing techniques which you can apply for enhancing the bandwidth, but that will not go up to that lower level, like 4 Hertz, 2 Hertz, like that.
Yeah. Actually, the attenuation is frequency dependent. The lower the frequency, the lower the attenuation. Higher frequencies are affected more by the attenuation. But the thing is, the vibrators create distortion at the low frequencies. So that's why, as the manufacturer claimed 1 to 250 Hertz, but we chose the 4 Hertz because we were mindful of the source generated noise. And when we had analyzed this noise, this was mainly from the near offsets. So if you just skip near offset, this noise will be totally gone. So overall, addition of low frequencies has much more benefit on the data quality. Like you mentioned that we have not conventional data. So whatever, like we have natural frequency of 10 Hertz. So that geophone also records the lower frequency, but in a tapered. So we can use in the processing the low frequency compensation for that. But that's in the case when which is the vintage acquisition, and we don't have the luxury to acquire and add more. But in the future, if you're planning at a survey, and because these vibrators are readily available, so we recommend that one should go for the low frequency, because this all over the world, this is standard nowadays. So it's not some kind of very high-tech technology these days.
Yeah, I think you're right. But I mean, this is very unfortunate, especially in complex tectonic regime, in compressional tectonics. What is actually it is happening with the seismic data is the noise contamination, for some reason, it is masking the signals, like you shown in your section also. So you are not able to interpret particular reflector which we think it has a good quality signal over there. It is somehow masked by the noise contamination. Now with this technology, maybe it will help us to identify that things more clean, noise free, and maybe there is a greater possibility to enhance that particular reflectors. I just want to understand, do you also calculate certain amount of proportion, like you mentioned, once you will inject source with a low frequency source, how much proportion of the low frequency it will decay till it will reach to the particular zone of interest which you want to
So what happens, the lowest frequency will decay the least. So what happens, your higher frequency is absorbed at the surface, and the lower the frequency, it has more penetration. So this is the main concept, that by addition the lowermost frequencies in the spectra, you have the maximum penetration available in the area. So like the 4 Hz, it will have minimum attenuation as compared to all of the frequency in the spectra. As you mentioned, this is also compression regime in the deeper part. But I think you are mentioning that we have on the surface fold belt area. For that, because this is in the Haran Basin area, on the surface we have dunes, so we can use vibrators, but in the mountainous area, most likely we use the dynamite technology. So some of this noise is coming from the vibrator source, but with dynamite, we have other type of noise that, like the ground roll and all the complexity associated with the fold belt on the surface. So for that, what we can do, we can use the low frequency geophones, but the dynamite source will be same. And with the introduction of low frequency, the processing also needs to be upgraded. Like the algorithms which are used for the conventional processing, they won't be applicable. You have to use the processes which are advanced and which tackle this noise in the data.
Hello, Javed.
Yes.
Thank you for such a nice presentation. Shafqat Ayaz.
Thank you.
I think all the questions have been addressed by this gentleman. Thank you. My only one question is, did you test any other parameter except this low frequency, like wide azimuth, maximum 4 offset, or maximum number of channels to acquire good quality data?
Yeah, that's what I told earlier, that in the previous campaigns, we acquired seismic data with 6 kilometers of offset. Then we did another campaign with 8 kilometers of offset. And in this campaign, we used 8 kilometers offset, apart from the low frequency So, and at the end of the presentation, we have presented the comparison for the different offsets. So if you see here, so on the right side we have seismic section with 6 kilometer offsets, to the same section, and on the left side we have the same section with 8 kilometer offset. And in the 6 kilometer we can still see these reflections inside package 5. So our point is that yes, far offset is important, that can add value to the seismic section, but the low frequency which can give us a better resolution at the deeper targets. I hope you answer your question.
Thank you.
Thank you very much, everyone. एक चीज़ जो है, अगर हम यहाँ पे नोट करें कि लोअर इंडस बेसिन से लेके हम कलात प्लेटो और फिर हम खरान बेसिन, मतलब हम यहाँ पे जो हमारे जीएनजी के जो यंग प्रोफेशनल्स हैं, वो ब्राउन फील्ड से लेके फ्रंटियर एरियाज तक के अंदर जो है, जो कॉम्प्लेक्सिटीज़ हैं, उनको रिजॉल्व करने की कोशिश कर रहे हैं. तो आई थिंक ये एक बहुत बड़ी अचीवमेंट है हमारी ईएनपी सेक्टर के लिए, जहाँ पे हम ना सिर्फ जो हमारी ब्राउन फील्ड्स हैं वहाँ पे भी हम टेक्नोलॉजी जो है, एडवांस टेक्नोलॉजी हम यूटिलाइज़ कर रहे हैं. हम फ्रंटियर एरियाज़ में भी जो है, जो कॉम्प्लेक्सिटीज़ हैं, उनको भी हम रिजॉल्व करने की कोशिश कर रहे हैं. तो आई थिंक अ बिग हैंड टू आवर यंग प्रोफेशनल्स, कीप इट अप. and we'll find more oil and gas for our country. Thank you very much. Assalamu alaikum.
This marks the end of this session, and I would now like both chairpersons to please stand up for the prize distribution ceremony. I would like to invite the first group led by Mr. Waqar Ahmed, along with Mr. Mudassir Zubair Khan, Mr. Waleed Jahangiri, Mr. Umar Farooq, and Mr. Ghulam Murtaza to please receive their shields on the stage. Mr. Waqar Ahmed. Mr. Mudassir Zubair Khan. Mr. Waleed Jahangiri. Mr. Umar Farooq. And Mr. Ghulam Murtaza. I would like to invite Mr. Shadab Ali Qureshi along with his team, which includes Tajammal Khan, Muhammad Kashif Khan, and Numan Ali. Mr. Shadab Ali, can you please come on the stage to receive your shield? Mr. Shadab, Mr. Tajammal, Muhammad Kashif, Numan Ali, is there anyone here? Anyone from UEPL who can collect the shield from their behalf? Okay, we are moving toward the next group. Mr. Javed Iqbal, Mr. Umar Farooq, Mr. Waqar Ahmed, and Mr. Atif Mir. So, Mr. Javed Iqbal. Mr. Umar Farooq. Mr. Waqar Ahmed. And Mr. Atif Mir. Now I would like to invite Mr. Muhammad Ma Siddiqui to please come on the stage and give the shield of appreciation to our distinguished guest, Mr. Arshad Palekar. I would like to invite Mr. Tariq Hassani to please come on the stage. Arshad Saab, sir, 2 minute stage pe rehna for the photograph. Tariq Hassani Saab, sir, can you please kindly present the shield to Mr. Irfan Hamid? Ma Saab, please aap bhi aa jaye for a group photograph, please. Thank you, distinguished chairperson. Thank you, sir. It was an honor to have you here. Thank you, sir. Thank you, Master.